So where does the escape velocity equation come from? This is an abuse of the conservation of energy, which states the energy of the system is always equal to the kinetic component plus the potential component. And in the last video, I showed that for a gravitational system, like this one where there's a big planet with mass m and a space shuttle taking off little m with some initial speed, this system has a potential of minus gm over r. And the kinetic energy depends on v initial at the beginning, but also just v in general as it changes. So we'll do 1/2 m v initial squared, and then this will be equal to the energy total. And now we have our initial equation, and I should put r initial as well. This is the radius at which it's taking off, or this could be further in space, as long as you define where the direction of v is away from the center of mass. And that means that if there's a component where, say, we're taking off here and our velocity vector is that way, as long as the component that's in line with the center of mass is reaching escape velocity, then the system will never return back to the planet. So if we go back to this example right here, let's go straight away. We have our unchanging energy total, 1/2 mv initial squared minus gmm over r initial. And we want to know how this system would act if it could never come back, which means that at r equals infinity, we want the kinetic component, which talks about this velocity going away from it, to be greater than or equal to 0. 0 is the minimum that it would take to get to r equals infinity and not have a velocity pointing back towards big mass m, which would mean that it eventually would come back. So now that we have this, we can, because energy is conserved, we can write another equation equal to it. 1/2 mvf squared this time, what our final velocity would be. And we discussed in the last video, the reason this is a negative quantity right here is because at infinity, it becomes 0. So minus 0. And this is equal to our energy total of the system, which would mean that if we set our final kinetic component to be equal to 0 to find the minimum velocity required for escape, this component would go to 0 as well, and we would just have our energy total equal to 0. So because of this, E tot equals 0, which equals 1/2 mvi squared. Oops, and then minus potential gmm over r initial, which means we can set them equal to each other, and we have 1/2 mv squared equals gmm over r, which would mean that we can now solve for velocity, which in this equation would give us the minimum velocity away from the center of mass that would result in the particle never returning back to the mass. So all we have to do now, little m's cancel, we're left with gm over r equals 1/2 v squared. Bring that to 2gm over r equals v squared, which means that v escape velocity equals square root 2g